Hi, my name is Matt Ostole, and I'm a developer relations technical artist at Epic Games. I helped out the Quixel team with materials and performance on their medieval game environment, and today we're going to talk about how we improved the performance of the project with a few simple changes that didn't dramatically impact the visuals. In the last video, we talked about how we established our benchmarks and budgets, tested performance consistently, analyzed performance to highlight problem areas, and how you can apply these principles to your project. In this video, we'll talk about how we diagnosed performance issues with our lights and shadows, and how I resolved them. First, let's look at our performance captures from the last video. If you haven't watched that video, be sure to go back and take a look to learn a bit more about Unreal Insights and how we gathered this data. If I dive into these numbers, I see that two of the numbers are a bit bigger than I planned for, and those are lights and shadow depths, in a lot, but not all of our shots. This tells me that we might have some dynamic lights that are visible in some places, but not others, and that some shots may have a lot of stuff casting shadows that may be causing some of those issues. Let's dive into the lights first, since this may help our shadow performance as well. Digging into the performance captures, I see that lights take up a disproportionate amount of time in this shot here. I'll raise the console command input with the tilde key and run the console command stat GPU. Yep, that's still high. I know we have a few dynamic point and spotlights in the scene, but how will I know which ones are causing issues? I should mention that we have dozens of these different stat commands, and you can read all about them in the links we've provided below. Stat GPU happens to be a favorite of mine since it gives you an overview of the costs of different rendering features. For this though, I'll use the GPU Profiler. It's a lightweight little utility that color codes and graphs out everything we did to render the frame. I can either press Ctrl-Shift-, to invoke it, or the console command Profile GPU. That raises this window, which gives us a visual breakdown showing the relative timings of rendering features. I'll sometimes use the GPU Profiler before jumping into something more detailed like RenderDoc, because sometimes I can learn everything I need to just from here. The scene value here is how long it took to render the scene. I'll expand that value out, and we can see the major passes here. I want to expand lights, and here I can see shadowed and non-shadow casting dynamic lights that are affecting this frame. Wow, almost all of those lights are the more expensive shadow casters. I can expand the shadowed light section a bit further, and it will show me each light and how long each light took to render shadows for. I can even double click on the lights to select them in the scene. There's a few causes for lights to be expensive, and I'll show you the 5 that came up while we were building this scene. Firstly, there's these point lights here in the forge. They're casting shadows, but because of how parts of the forge are occluded, we can really only see the effects of this light when we're up close. For this one, I set the max draw distance, so it isn't considered at all beyond a certain range, and the max distance fade range, so that it increases in power as we approach it instead of sharply turning on and off. Secondly, we've got this light here that's used in our end sequence cinematic moment. If you look, we're paying to render the light, but look here, the intensity is 0. This one's easy. I just went into the sequence for that end moment and added a visibility track to turn on the light before we ramped it up and set the light's default visibility and hidden in-game to off. Thirdly, there's this spotlight here that I know the artists are using to really sell the burned down building, but its attenuation radius is really quite high. That means we're trying to resolve the light and cast shadows for it from here in the center of the village all the way through the tree line and beyond. We can bring in the attenuation radius of the light quite a bit so that it's only affecting the parts of the scene that it needs to, and of course I'll set its fade values. Fourthly, there's this really subtle fill light we added to the area behind the house. Its radius is already pretty low, and it looks like the artists set the fade values already, but it's casting shadows, even though there's not much to cast shadows from in its radius, so I'll just turn that off. Finally, I saw the lights from these lantern blueprints in our captures. I know the artists wanted these to be a bit more of a dynamic element. For example, they can sway back and forth in the breeze, but the light had a function on it. I knew that light functions are particularly expensive and should be used sparingly because it automatically treats the light as if it was shadow casting and dynamic. That function, for example, was only flickering the light intensity, which isn't the most optimal use for a light function. Instead, and since this blueprint already ticks to drive the swaying motion, I used a timeline to randomly modulate the intensity of the light as if the candle was flickering, and I will definitely set the fade distances on this light. Armed with all of these different cases where we weren't using lights as efficiently as we could, I trawled through the scene to make sure each and every light had fade distance set an appropriate attenuation radius, made sure we're using light functions effectively. For example, the light from the well has a caustic effect on it and has a fairly low attenuation radius, and ensure that only the lights that really need to are casting shadows. These aren't hard and fast rules by any stretch of the imagination. There's plenty of factors that could change how you'd approach optimizing dynamic lights for your scene, and you should take into account the specific needs of your project. This is just what worked great for us. Oh, hey, speaking of shadows, let's talk about the directional light. In many cases, you'll be going along working on your very large open world scene. Everything's looking great, and you've never made anything more beautiful. You start testing your scene, climb to the top of the mountain, and oh, what's that? Your shadows have a hard stop a ways off in the distance. That's alright, you think, because you know that you can just raise the dynamic shadow distance on your directional light and you get your shadows back. See? Perfect. Except now you're running about 15 frames per second and you haven't even started drawing shadows out far enough to grab the mountains on the other side of the valley. Worse still, the shadows close to the camera are now blurry. What's going on here? In Unreal, dynamic shadows cast by the directional light use what's called cascading shadow maps. Basically, we break up the scene forward from the camera into a number of cascades, which are controlled by the directional light, of a certain size. Then, we draw a depth map from the point of view of the directional light and use the information to figure out what is or is not in shadow. Let's take a look at this sample scene. We've got 4 cascades, a dynamic shadow distance of 10,000, and a distribution exponent of 1. This means that roughly each cascade covers 2,500 units. I've spaced out each of these trees so that there's only one per cascade, along with a tree nearby to cast some noisier shadows close to us. As I increase the dynamic shadow distance to get shadows on those further trees, we can see the shadows cast from the nearby trees start to get blurry. We're effectively decreasing the texel density of our shadows. To solve this, I could increase the number of cascades. That way more cascades would cover the same distance, thereby bringing my shadow texel density back up. This method has the drawback of increasing both the memory needs and taking more time to render. I could tweak the distribution exponent to prioritize resolution on shadows nearer the camera, but we're still drawing dynamic shadows way off in the distance. I can't really see the details of the tree swaying in its shadow, let alone the shadows of the individual leaves as if they flicker, but I'm still paying to draw them, which is my cue that there's probably a better way to do this. The good news is that there's a better way to handle shadows of distant objects that uses pre-computed mathematical representations of static geometry to cast shadows instead of the polygons and materials. These are called distance field shadows. There's 2 trade-offs with this method that I think you should keep in mind. 1. Since we don't compute a mesh's distance field at runtime, world position offset effects won't be visible, but at the distances where we employ distance field shadows, this will be negligible. 2. Each static mesh will have some additional memory overhead attached to it to account for its distance field representation. For lower resolution distance fields, this can be negligible, but can increase exponentially as more definition is required. We'll need to set Generate Mesh Distance Field to True in our project settings, and I'll leave some links in the description so you can learn more about mesh distance fields and all the really cool effects that you can do with them. When I set this up for our project, I brought the dynamic shadow distance in to really close to the camera. We were taking a big performance hit drawing so many actors in our dynamic shadows, so I wanted to make sure we were getting what we paid for, so to speak. I activated distance field shadows on the directional light as well. Since distance field shadows will cover the gap between our dynamic shadow distance and the distance field shadow distance, I set that value to be about as far away from the camera as the back row of trees is from here. I just scooted the distance up until I just started to see the shadows where I wanted them, and not a unit further. This leaves out, however, the mountains off in the distance. I don't want to use distance field shadows to reach them since they're so far away from the rest of the stuff in the scene, and we can't see the shadows between here and there either, because they're covered by the tree line. I've got one last trick up my sleeve, and that's the Far Cascade. It's an additional cascading shadow map that covers the distance between the distance field shadows and the Far Cascade distance. By default, this value is set really high, so how do we make it more performant? Well, we do that by limiting the number of actors included in the Far Cascade. Whereas dynamic shadows are opt-out, you have to turn off shadows on an actor. The Far Cascade is opt-in. You must choose which actors cast far shadows. First, in the directional light, I'll set the number of Far Cascades to 1. For this project, I knew that I wanted the mountains off in the distance to cast shadows on themselves and each other, so I'll select those actors and click the Far Shadow checkbox. Finally, I tuned the far shadow distance to ensure those mountains were casting shadows. This pushed the distance out a little further than the default, however, this was significantly less expensive than any of the alternatives. I used the same method I described with distance field shadows. I just slowly pushed the distance up until I got the shadows I wanted. So to summarize, it's best to use cascading shadow maps closer to the camera for highly detailed or moving shadows. If you can afford the memory overhead in your project, you can use distance field shadows to extend the distance at which dynamic shadows are rendered, but at a lower level of detail. Finally, you can use the far cascade to explicitly ensure large structures are casting dynamic shadows at a sensible distance. Of course, as with dynamic lighting, there's plenty of different ways to optimize the shadows in your scene, and you should take into account the specific needs of your project. These techniques worked great for us given the size and composition of the village. There was one last factor that was hurting our shadow performance, and we tracked it down to distance field shadows. It turned out that a lot of our small foliage were casting distance field shadows when, more than likely, they were merely ground cover or other smaller pieces that weren't adding anything to the scene by casting shadows. To turn that off, I went to the content browser, filtered by foliage, select all, right-click, asset actions, bulk edit via property matrix, and pinned Effects Distance Field Lighting, and unchecked that for the foliage I thought wouldn't need to be casting shadows off in the middle distance. There's more to come with our foliage, so stick around for the next video to see what other optimizations we made. Tuning dynamic shadows is a tricky endeavor, given the vastness of factors involved and the options at your disposal. At the end of the day, though, it's all about trade-offs. Choose what's best for your project, and don't be afraid to experiment. I hope this has given you a little more insight into how we tuned the lights and shadows in the medieval game environment. Be sure to check out the project on the Unreal Engine Marketplace to get a look at how we implemented all of these optimizations. Thanks for watching.